Thank you. Today's topic is a little different than the topics that we have here before. So I hope that someone of you will be interested in this topic. I hope. So let's start. Today's topic is anonymity in MACI. When we say MACI, we think that MACI is a minimal anti-collusion infrastructure. This is project from Ethereum Foundation, and my team, 3327, obtained a grant to add anonymity in MACI. When we said anonymity, we think that we want to add that no one cannot know how voters voted. So anonymity is in a relation with voters. But before we go there, how MACI actually works and what is done so far in MACI and what we want to add in MACI, I think that is very important here to note that it's very difficult to create voting system that is completely resistant to collusion. And we want to have a voting system where we cannot manipulate with votes, when we cannot censor the votes, and also to have privacy and anonymity of voting. So naturally question arises, is it possible to make this such a voting system, perfect voting system, without collusion? And I think the answer is yes. And I think that this answer is related with MACI. So let's start. We can tell that MACI is an application which allows a user to have on-chain voting process. And this voting process is not completely collusion resistant. But I think that MACI have made a big step in this way. And with adding anonymity, I think we will get a voting system that is completely resistant to collusion. Or we will be so close. From technical perspective, we can see that MACI is collection of smart contracts, of course, zero-knowledge circuits, and TypeScript packages. And I think that is important to say that initial idea came from Vitalik. And we said before, but I think it's important to remember that MACI currently reduced the bribery and disables censor voting. Today, I think that is very important to answer on these three questions. The first one is how actually MACI works. Who can see how voters voted, and is it possible for voters to cancel the vote if, for example, we have a voter which was blackmailed? Okay, let's start. How MACI works. We have here two different roles. The first role is we have users on voters, and the second role we have coordinator. We have one single coordinator, and this coordinator is trusted coordinator. So voters need to sign up first with theirs public key, and theirs public key plays a role of their identity. After sign up phase, voters need to vote, and before they send the vote to MACI smart contract, they need to encrypt that vote. And when they encrypt that vote, we call it message. And they send the message to MACI smart contract. After that, it's important to say that they encrypt the message using shared key, and only voter and coordinator knows that shared key. Okay? So when coordinator decrypt the message, he can decrypt the message because he knows shared key, he gets the vote. But to be more precisely, we want to explain what is the message. The message, to get the message, we need to put some things together. For example, we need to put new public key, vote option, vote amount, and some other variables that is not important for us today. And we create a command. when we create a command, user needs to sign this command with his public key. When he signs this command with his public key, he needs to encrypt command and his sign to obtain a message. And this message will be sent to MACI smart contract. And why this is important? Because voter in this message can change his public key, and also he can change his vote in one message. And this is important. If user was blackmailed, he can prove to blackmailer that he vote for option that blackmailer wants to vote, but that message will be invalid. And I think that the best way to understand this is to give you one example. For example, we have a voter or user, how do you want, that has public key 1, and he used that public key in sign up phase, okay? After that, he wants to vote, and he wants to vote for option 1. But he was blackmailed to vote for option 2. So, firstly, he will send the message. He will write here in the field new public key 2. He wants to change his public key. And he will write here option 1 because he really wants to vote for option 1. After that, he puts all this stuff together to get a command, sign this command with his public key 1, and after that encrypts the sign and command to get the message. And send this message to MACI smart contract. Okay? When coordinator decrypts the message, he will update his state. He will write that this voter changed his public key, and his new public key will be public key 2. And he will update state 3 with the vote for option 1. After that, user can vote again. He can write here public key 1, the old public key. And he can write here vote for option 2. He will put this stuff together to get a command. He will sign it with his public key 1. And after that, he will encrypt the command and signature to get the message. And then he will send the message to MACI smart contract. When coordinator decrypts this message, he will show that the public key that user use to sign this message is not the same like his previous public key, and this message will be invalid. But beautiful thing here is that the voter can decrypt this message and can prove to the blackmailer that he really voted for option 2, and blackmailer cannot know that this message was invalid message. So user can vote for option they want, and blackmailer cannot know that user didn't want for the option that blackmailer wants to vote. Let's study encryption. In MACI, we are using elliptic curve Diffie-Hellman encryption in order to obtain the shared key. We will use generator point on elliptic curve. This is G, and we will use private key of a user and private key of coordinator. To get public keys, we need to multiply this private key with generator point on elliptic curve. When we multiply this, we will get the point on elliptic curve, and that point will be the public key. It's very easy. And how we can get the share key? We told already before that only user and coordinator knows share key. When user can multiply his private key with public key of coordinator, because public key of coordinator is public for him. But coordinator can do similar thing. Coordinator can multiply his private key with the public key of user. Okay? And both will obtain the same. And this is share key, and this is 1 point on elliptic curve. And how we get this? Because we use very elegant property of elliptic curve. And that property give us this equality. So only user and only coordinator can know the share key. Of course, the security of this algorithm lies in difficulty to calculate discrete logarithm. When the voting is over, we will have coordinator which will enter the scene. Coordinator will need to make a zero knowledge proof that he decrypt all the votes correctly and that he update state 3 correctly. After that, he needs to collect all the votes and to make zero knowledge proof with outcome of the voting. So every user can be sure that this voting was done correctly, okay, but no one will know how voters voted except coordinator. Remember, coordinator can decrypt everyone's vote, so coordinator knows how voters voted, okay? Even if coordinator is corrupted, he cannot add the extra vote, he cannot censor the vote, because if he is trying to do that, he will not be able to make true valid zero knowledge proof. So we will not have finished voting, never, but we can be sure that coordinator cannot publish false results, and this is very important. In the previous slide, we explained everything what is done so far in MACI. And I think that the big problem is because coordinator can see how voters voted. And if you are good with coordinator, he can pass you information and you will know how voters voted. And this is good for you, but it's not good for voters. And because of this, I think that is a big problem that we need to solve. And we solve it adding anonymity in MACI. So how we could achieve this thing? What do you mean? It's easy. We want that coordinator cannot see the link between the old and new public key. Okay, so what we need to obtain this, we need to have new type of encryption. We will using L-gamma encryption. We need re-randomization, and of course we need zero knowledge proofs. So we will use the same notation as we used before. G will be generator point on elliptic curve, and we have private keys of user and coordinator and their public keys. So the user is person who will encrypt the data for coordinator. The user needs to do, first thing that he needs to do, he will pick some random number from interval, and after that he will multiply this random number with a generator point on elliptic curve to obtain big X. I want to note here that if we want to go and obtain little x from the big X, we cannot do it because this is discrete logarithm problem, okay? Big X will be sent to coordinator from the user. And we have one more thing to do here. We need to map the message on elliptic curve. And this is hard problem. For example, if we want that some message, some number, some secret map on elliptic curve, and we want to do that in the way that first coordinate of the elliptic curve point be this message, we knows how equation of elliptic curves like, and when we want to calculate the second coordinate, we can get that that second coordinate is not in the final field that we use. So it's a problem. And how we solved this problem? Well, our message will be some states, and we have finite numbers of states. So we can find bijective mapping of states to elliptic curve. For example, we can map 0 to infinity point. We can map 1 to base point on elliptic curve, okay? And this is bijective map, and we can go in vice versa, okay? And we done it like that. Okay, after that, user can calculate this. This is a public key of coordinator. He knows little x, this is a secret, and add this point on elliptic curve and obtain ME. And this is mistake. User will send ME and x to coordinator. After sending this, coordinator needs to decrypt the message. How he can do it? Well, this left hand side, coordinator cannot decrypt because coordinator doesn't know little x, it's a secret. But we have equality here, and coordinator can compute this. He knows big X, and he knows, of course, his private key. So on this way, he can obtain this, and after that, because he know ME, user send them to, he can obtain the point M, which represent message on elliptic curve. And in this way, coordinator can decrypt the message. It's important here to note that using L-gamma encryption, coordinator can decrypt the message without knowing public key of the user. And when we used share key, we can do that, because to decrypt the message, coordinator needs to know public key of the user. And here, he doesn't need to know. Of course, the security of L-gamma encryption lies in difficulty to calculate discrete logarithm, like we have it before. And we said before that we will need to use re-randomization. Why this is important? Because we usually use re-randomization when we want to convey the same message, when we have two ciphertext, but we don't want that ciphertext be connected, okay? And that function that randomize existing ciphertext can be decryptable using the same way when we decrypt existing ciphertext, and this is important too. I think that maybe we don't need to go through this, if it is okay for you. So, what we want to add? We want to preserve two nice features. We want that every vote to be encrypted and stored on chain. We want that user have ability to change his public key in order to prove blackmailer that he really vote for option that blackmailer wants. Of course, we want that message to be invalid. But we want to add one feature, and that is that coordinator cannot know how voters voted. So, how we will use all that we said already, L-gamma encryption, decryption, re-randomization. Let's see. We don't want that coordinator can see the link between old and the new public key. So, we want that user make zero knowledge proof that he knows private key for his old public key, okay? And we will need to add two new sets. One of them is set of deactivated keys. User needs to prove that he knows private key for old public key that is in the set of deactivated keys. So we will need to have membership proof. And of course, here we need to be more careful because we want that user can generate new keys only once. And because of that, we need to add nullifiers, and we need to add the set to store the nullifiers. And we need to add some more things. We need to add 2 more types of messages. The first messages is for deactivation public key. To deactivate the old public key, user needs to send the message to coordinator, and this message will be encrypted using LGAML encryption. After decryption, coordinator will add this public key in the set of deactivated key if this public key exists, and he will also add encrypted state in the field, in that field where is public key that we want to deactivate. If anything goes wrong, coordinator will put in this set public key, but he will change the state and the state will be false. So after that, user can create new public key proving that he have a public key in the set of deactivated keys. So what user needs to do? User needs to make zero knowledge proofs that he knows private key for the public key that is in the set of deactivated keys. And the output of this circuit needs to be nullifier. Nullifier is hash of private key and needs to be re-randomized message, because we don't want to see connection with this message with old public key of user, and we don't want that coordinator knows who is that user. And because of that, we need to use re-randomization. Okay. When user send the message, coordinator decrypts the message, and if everything is okay, if proof was valid, if a nullifier is not in the set of nullifiers, coordinator will update state, and he will add this new public key and this encrypted state. If anything goes wrong, he will add also this public key, but the state will be false. And with this, we really obtain that coordinator cannot know how voters voted, so we get anonymity in voting like we want. And that's it. Thank you.
We're welcoming questions.
So if all this happens on chain, that means transactions are signed, and they are signed with my private keys of my address, right? So I wonder, I'm trying to put myself in the worst case scenario of blackmailing, right? If I cannot know who you have voted for, but I still will know if you voted or not, right? So maybe the blackmail could, do you think the blackmail could turn into forcing people not to vote? Because if it's on chain, I can see that your address, your wallet has vote one way or the other, right? And if I cannot control the direction of your vote, maybe the blackmail turns into, okay, I'm gonna stop you from voting.
I think that I understand what you are talking to me. If I understand good, probably the blackmailer will know how these things are working. And I think that maybe the best way is to have a large enough set where we have all keys deactivated to obtain anonymity. And maybe we can add, when sign up users, old public key to be deactivated.
When you're talking about keys, I think
Yeah,
you're
yeah.
talking about two different set of keys, right? The keys that initially were the shared keys, but all these transactions need to be signed in Ethereum with your wallet, right, with your address, right? And that is something that we cannot hide. So I guess my point here is the identity of the voter is still expressed as an Ethereum key, right, that goes into every single transaction that goes on chain, right? And we cannot hide that. That is still public, right? So there is still a visible signal that links the person, the individual, to the transaction performing on chain.
Yeah. Yeah.
Mm-hmm. Okay. Okay.
Then it gets more complicated. Like who controls the relayer?
Okay, but now it's clear. Thank you.
Thank you.
Cool. Any more questions? Do we want to vote on it? Okay. Thank you, Maria.